Okay, well, season's greetings to everybody. We've got 16.5. What a way to wrap up right before break, doing some vector calculus fun. All right, so 16.5, we're going to learn two new operations that we're going to be using over vector fields. Remember what a vector field was, guys. Very often it would be written with a capital F, and you might see a P, a Q, and an R, which are all functions of X, Y, and Z. But the whole idea behind a vector field is we could put in an ordered triple and then get a vector assigned at that point. And that vector could have a very different magnitude and direction from point to point. And vector fields could represent what is occurring in gravitational fields, fluid flow, electrical fields, magnetic fields, and so forth. But we're going to learn of two operations that we can apply on these vector fields. And I don't think we can appreciate them for a little bit. We're just going to learn the mechanics of it today. So let's say we do have what I highlighted, some force field, a vector field perhaps, and we do have partial derivatives existing. Then the curl of F, and that can always look a little odd. You know, are we really just calling this operation the curl? Yeah. And I hate to say this too, I think very often kids might wonder, ooh, is this built into the TI-89, this operation? Sadly, no. Oh my goodness, it's very disappointing to see it's not. But what is this curl? If you'd say, I'd like to take the curl of a vector field or even of a force field. Well, my goodness, it's in this box. It's going to be a vector. And my goodness, you can see all these partial derivatives from F coming into play. So what you're seeing is a partial derivative of r with respect to y minus partial derivative of q with respect to z. That's your I component, and similarly we have very familiar or similar quantities out in front of j and k. Well, my goodness, is there a way to remember that? I mean, you could memorize that A, but there might be another way to just work it out where we wouldn't have to commit this to memory. And that's what the author suggests and what we traditionally do at this point. We're going to try to find a way to write this all out. And to do that, we need to talk about the vector differential operator, which we call del. Del is this upside-down triangle. Usually kids are like, wait a minute, we've seen that before. That was what was in front of the gradient. And indeed, it is. It is exactly what's out in front of the gradient. And if you look right here, we'd say I, partial derivative with respect to x, plus j, partial derivative with respect to y, and then plus k, the k vector, partial derivative with respect to z. Now what seems odd is you'd say partial derivative of which function? Well, that's left empty. It's saying, well, we're going to have to apply some function in there. And the del operator is going to come into play right here with curl. The curl of a vector field is del cross F. Del cross F. Now I'd like to show you how we can work out the cross product by hand. We talked about doing cross products by hand way long ago, back in our vector chapter of 12. And what we saw is that we need a 3 by 3 determinant. So the curl of F is this 3 by 3 determinant. Here we have I, j, and k. And then we're going to put in del. Now what's del? Well, it's the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Notice I am not putting any particular function in there. I'm just writing the partial derivative in this form. Well, then what do we put underneath? Well, we have f. And remember, F is a vector field. And we go back up to how F was defined. It was P, Q, and R. P for the I component, Q for the J, and R for the K. So if you were to do this 3 by 3 determinant, you would arrive at the curl of F, the curl of that vector field. Now, you might remember yesterday, right at the end of class, I very quickly talked about how we could do a 3 by 3 determinant. And you might remember what we did. And I'd like to lightly, just go over that with you. Tell you what, I'll go to a thin pen and say when you want to find your I component, you can cross out a vertical column there where I is, cross out that row with I, J, K. We always have that. And notice what is left. I'm going to erase this in just a moment. What's left when we cross that out? Well, a 2 by 2 determinant. A 2 by 2 determinant. Now, here's what we do. We're going to say, well, wow, look at this. For I, you guys remember how to evaluate a determinant. We were doing that with the Jacobian, weren't we? You were even doing that yesterday. We'd say, well, isn't it going to be this left diagonal, partial derivative of, what do I plug in here? Partial derivative of R with respect to Y. Then what? For this other diagonal, before I even get to that, I have to minus partial derivative of Q with respect to Z. Now, are we multiplying? Oh, I guess you could say we're really just plugging Q in there. Del allows us to multiply a function in there, and it's saying really plug it in. That's effectively what's happening. But look at this box right above. That's exactly what is going in for our I component. You see that? So then you'd say, now what about J? Well, this is where we've got to be a little bit careful, and this is always a little odd. Now, J, we could again go to a thin line here and say, well, cross out the top row, cross out the column with J in it. Let me also erase everything else. Remember what we said yesterday. This is where technically we'd have a minus, where the signs changed. We'd say minus. And now what is left, what remains as we have this? You can see we have partial derivative with respect to x and r if we were to go in a 2 by 2 determinant. We could say partial derivative of r with respect to x. Now immediately kids will say, wait, that doesn't look right. Hold on, we're not done yet. Look, then we come this way, we'd say minus, we'd have partial derivative of p with respect to z. Now don't forget you could distribute that minus back in, and if you did, then you get what is listed above in that box with we highlighted. Okay? So that's certainly what we could do very, very quickly. Then what? We could say finally for our K component. Well, again, we could erase all this. The more you do this, the quicker these become. The first time you're doing it, it goes rather slowly. We're going to go back. We're not changing the sign. The only sign we change is the J component. And then what? Well, we'd say for K, well, look right here. We'd have partial derivative of Q with respect to X minus, here we'd have partial derivative of P with respect to Y. And now if you double check comparing what was listed up in that box at the top, you can see we get that exact representation, especially when we just distribute the negative there. That's how to find the curl. Now, like I said before, the curl of a vector field, right now it might not have as much meaning to you. In a few minutes, we'll even talk about how we can use it in real life. But first, today's homework, a lot of it, quite a bit of it, is rather mechanical and rather computational. And you'll be given a vector field and you'll be asked, hey, would you find the curl? And very quickly we'd say, well, my goodness, that means just take a 3 by 3 determinant. Exactly. Let's do that. Now, by the way, I'm going to try to streamline this a little bit. I really slowed down the working out of the curl just a moment ago. But what I'd like to do right now is work through it a little more quickly and talk through. Now, your P in this problem, you could say, is xz. Sorry. We can say for our J component, it's xyz. And for our K component, we'd have negative y squared. I think what I want to point out to you very quickly is this, that if we were to find what goes in front of I, and I'm going to list this up above. You could say very quickly, look at this left diagonal. And again, just starting off, we're just focusing in right in here. What would that left diagonal be? Now, here's where I want to be honest with you. Maybe the first time you do it, maybe you write this all out. But I think very quickly, just going on a left diagonal, you can say, what's the derivative of that negative y squared with respect to y? And what would we say our answer is? Hopefully negative 2y, right? See, the more you do this, you just immediately jump into that and say, I'm going to just take that derivative with respect to y. And then we come over here to our other diagonal, and we'd say, do you know what? I've got to take the derivative of x, y, z, but with respect to z. And what would that be? xy, and I'll just say minus xy. That's your component of I. That's what goes out in front of I. So then what? Well, then we jump over here and we'd say, well, let's find out what's going to go in front of j. We could keep a negative out in front, and there are some authors that even do that, and that's perfectly fine. Let me even erase this out. We can say, well, let's just come right down here. We'd say, hey, what's our partial derivative of negative y squared with respect to x? What's that? 0. See, right now I'm writing that out, but so very often kids are going to be like, hey, I can just do that in my head. And then look at this other diagonal that wasn't highlighted. You could say partial derivative of xz with respect to z. What's that? Just an x. And we can distribute that negative in just a second. Then what? We'll come over here to our k. And so very often, all kids have to do is just, very lightly, and I think maybe that's the thing to do, just lightly cross out that row. Sometimes kids even say they bring an extra pencil and they just put it over that row so it doesn't even block into their view. And then they'll just say, well, I just look at these diagonals, like right here, and I'll just do those partial derivatives immediately. And yeah, you can do that. Look, I've got the partial derivative of xyz with respect to x. What's that? Just yz. And then I'd say, well, what's my other diagonal? My partial derivative with respect to x, but xz with respect to x. What do we get? Just a z, right? Is it y? ddx. I'm sorry, I lost it. Oh, yeah, right here. I miscopied it. That's with respect to y. So sorry. Thank you, guys. Good thing you're here. What is that, then? Even more simply, 0. I erased it and fixed it up. Okay, so what's our final answer? Thank you so much, guys. Negative 2y minus xy I minus a negative turns into a plus x. That's j. And then we could say plus yz. And you could put parentheses around these if you'd like. And here's vector k. Look at that. That's your curl. And that's all you need to do. The curl of a gradient in our next theorem, you could prove this very quickly. It's going to be 0. And then following this up, if f is conservative, meaning that function f is equal to the gradient of little f, the curl is 0.